Hello everybody and welcome to another video on the channel. Today we will be talking about related rates in calculus and understanding pretty much how quantities can change together. The exact definition of related rates is problems involving two or more quantities that are changing with respect to time where the rates of change are connected. Basically, we have one quantity changing with respect to time, but we also have another quantity changing, but we can also find a way to relate both of those quantities changing. Normally, they're related by an equation or by geometry. So, a few real-world examples is a balloon expanding, radius, surface area, and volume are all changing, all. Ladder sliding, where a ladder sliding is where angle and height are both changing, and a tank where you're filling water in it is where height and volume are both changing. Normally, there's pretty much only 4 steps that we're going to be using to solve these problems. The first step is writing an equation relating the variables. Basically, if we have xy, we'd write x dx by dy plus dx by dt plus dy by dt is equal to 2. And that's very rare that would happen. That sounds like something more from differential equations than calculus, but I think you get the point. The second is to differentiate both sides with respect to time, or t. And number 3, substitute known values. And number 4, it's to solve for the unknown rate using algebra, and it can get very complicated. We have a few common derivatives and a few key mathematical tools that we're just going to be using time and time again to solve these types of problems. The first one is the chain rule. Also, I have the chain rule over here, but the chain rule with respect to time also is a sort of implicit differentiation where you have f dash x but also times dx by dt. And this one is just the pure chain rule that we might need to use for functions even inside the implicit differentiation. The other two formulas are the derivative of the area of a circle and the product. Let's move on to our examples, and our first example, which is a spherical balloon is being inflated. When the radius is 5 feet, the radius is increasing at a rate of 2 feet per minute. How fast is the volume increasing at that instant? So, our given information, which I noted down over here, is the radius is equal to 5 feet at that time, and dr by dt is equal to 2 feet per minute, and our goal is to find dv by dt. First, we have to state the volume formula, because when we differentiate the volume, we'll get the equation required to solve our problem. So volume is equal to 4 divided by 3 multiplied by pi r. So what's next is we have to differentiate this. So we have dv divided by dt is equal to 4 pi r cubed. 4 divided by 3 multiplied by 3 will just be 4 pi multiplied by r squared for the power rule, then multiplied by the derivative of r with respect to t. So dr by dt, and that's pretty much the chain rule / a sort of implicit differentiation. Next, we need to substitute our values. So dv divided by dt is equal to 4 pi multiplied by r squared, so that'll be multiplied by 5 squared. Then, after we multiply that by 5 squared, we have to multiply that by dr by dt, which is 2. So, what happens is we have 4 times 25 times 2, which is going to be equal to 200. And then, since we have pi, that's going to be equal to 200 multiplied by pi feet per minute. Now, I'm not going to put the units here. What I'm going to do is I'm going to paste this down, all the steps over here. And over here, if you look at the steps, what we'll get, I'm going to put my cursor over here to show you where the text is at. dv divided by dt is equal to 200 multiplied by pi. So I'll just say 200 pi with where we write out the name, then feet per. So now that we have that, it's gonna make this a little darker, bold it. So that is our answer for our first problem. dv by dt is equal to 200 pi feet per minute. Sorry, feet cubed per minute. Very big difference. Our solution also shows a very similar thing. So volume of the sphere is 4 by 3 pi r cubed. Then we differentiate and substitute and solve for our values. Our second example is that a 13-foot ladder is leaning against a wall. The bottom of the ladder is sliding away from the wall at 5 feet per second. How fast is the top of the ladder sliding down the wall when the bottom is 5 feet from the wall? So given information is we have ladder length is 13 feet at that point. The dx by dt, or the horizontal rate of change, is 5 feet per second, and x is equal to 5 feet, basically where the bottom is 5 feet away from the wall. So what we want to find is the rate that the top is sliding down, or dy by dt. The first thing that we need to do is figure out what y is exactly. So if x is equal to 5 feet, that means using the Pythagorean theorem, we have 5 squared plus y squared is equal to 13 squared. And if you recognize this as a Pythagorean triplet, basically 3 numbers which could be 3 sides of a right triangle, you'll realize that y is equal to 12. Alternatively, you could evaluate it like this. Y squared is equal to 13 squared minus 5 squared. So y squared is equal to 169 minus 25. So y squared is equal to 144. Take the square root of that and you get 12. So y is equal to 12. That is y. So now what we need to do is differentiate dy by dt. Sorry, not dy by dt. So what happens now, after we've evaluated y, not dy by dt, is we take the Pythagorean theorem, basically x squared plus y squared is equal to 13 squared, because that's the constant length of the ladder. What we need to differentiate this. So what we get right afterwards is we have x squared, the differential of x squared is 2x times dx by dt. Then we have plus 2y times dy by dt. It's equal to 0 because the 13 squared is a constant, so that's just equal to 0. Now we have to solve for dy by dt because that's the quantity we're looking for. So first we'll bring the term with dx by dt to the other side. So 2y multiplied by dy by dt is equal to negative 2x multiplied by dx by dt. After this, we divide both sides by 2, so that just becomes y dy by dt. Then, since y is equal to 12 and x is equal to 5, we get dy by dt is equal to negative 5 over 12 multiplied by dx by dt. And dx by dt is equal to 5 feet per second, so we have dy by dt is equal to negative 25 by 12, because negative 5 by 12 multiplied by 5 is equal to negative 25 divided by 12. So there you have it. There's our solution to our second example. Let me make this a little smaller, and let me actually write the real answer that's not just a number, because it has to be a unit. So dy by dt is equal to negative 25 divided by 12 feet per second. So that is the rate of change of the heights where we have both x and y. Now what I'm pretty much doing is I'm actually showing you very common problems over here. This is stuff you'll find all the time in exams and textbooks. And there are more types of problems. So in fact, my next video will be a continuation of this, where I talk more about some of the different types of problems, like flow problems and shadow problems, but I'll explain them later in this video. But first, this is our solution to our example. It has very similar steps. Find y when x is equal to 5, differentiate it with respect to time, and substitute and solve the equation. So our answer is the top slides down at 25 by 12 feet per second. Here is a quick practice problem with the solution on the side. So this is a flow problem, which I'll explain in a second, and it says that water is flowing into a conical tank, basically a tank with the shape of a cone, and it says vertex down, so the point will be down on the bottom at 8 feet cubed per minute. The tank has a height of 12 feet and a top radius of 4 feet. How fast is the water level rising when the water is 6 feet deep? And here's a small setup where we have the volume of a cone and bisimilar triangles, or just how a general cone works when you scale it up or down. Since it has properties that are quite similar to triangles, a few of them at least, basically the radius is going to be 1/3 of the height all the time. And here's the solution, which actually utilizes that. Here are a few common geometric relationships that are very essential to remember. You will find this a lot in problems, and if you forget one of these, it'll be very difficult to find it, unless of course you have a cheat sheet or anything. But these are very essential to remember, or at least understand which shapes they relate. Here are a few common mistakes that I've seen a lot of people make, and I've made a lot of these myself too. The first is don't substitute values too early. First, you have to differentiate everything and simplify. Then you can substitute all your values and use a calculator probably to figure out the rest. Number 2, watch your signs. Pay attention to whether quantities are increasing or decreasing, because you can get completely different answers whether quantities are increasing or decreasing. Then, number 3, make sure to include units in your final answer, and this can actually save a lot of points on tests, because there are many times where people will take off points if you don't have units. And number 4, define the variables clearly. Specify what each variable represents so there's no confusion on does this variable mean this or that or this or that, etc., etc. Now there are a few main types of related rates problems, and that's what I was talking about explaining later in the video. So the first is geometric, where we have expanding or shrinking shapes, or moving objects, or just anything that has to do with scale. The second is motion, objects moving along paths relative to each other. The third is flow problems, which was the practice problem we saw, where liquid is filling/draining containers. And the fourth is shadow problems, where they're changing light sources and shadows. Normally, these will involve a lot of similar triangles, especially when it comes to two people or two different objects exerting different shadows. Here are a few key takeaways. First, the related rates connect the rate of change of related quantities. Number 2, always differentiate the relationship equation with respect to time. Number 3, use the chain rule and implicit differentiation. And number 4, substitute known values only after differentiating. And thank you so much for watching this video. I'm so happy you watched to the end. And if you found my content educational and entertaining, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this, so you don't miss any more videos and you always stay updated on when I'm posting. So thank you so much. See you in the next one, and bye-bye.